All right, let's dive right into this explainer. Imagine we freeze time at the exact millisecond a striker's boot connects with the ball in a Boston stadium during the 2026 World Cup. We're going to explore exactly how that physical impact instantly becomes a global digital event. Millions of us are going to be sitting in our homes, offices, and fan zones, enjoying these matches across the US, Canada, and Mexico. But behind every single passing goal is an absolutely extraordinary feat of network engineering.
So how exactly does that one single kick instantly reach billions of screens? Well, the secret is this staggering, completely invisible data infrastructure that connects the pitch straight to your living room in mere milliseconds. When a striker finds the back of the net, a fan in Tokyo and a commuter glued to their smartphone in London are reacting at the exact same time. How? Because what feels like a simple football match playing out on your screen is actually a massive, high-bandwidth, global fiber optic operation running flawlessly right behind the scenes.
And to make this magic happen, a highly coordinated broadcast army actually starts stress testing the architecture hours before the whistle even blows. At T-12 hours, massive fiber trunks are hooked in. By T-8 hours, the team is literally flooding the data pipelines to simulate extreme loads and guarantee absolutely zero packet loss. And 4 hours out, all the replay servers are fully synchronized. They do all this because at this kind of scale, failure simply isn't an option.
All right, so the whistle blows. Down on the stadium floor, we're talking about a highly coordinated mechanical ballet of at least 45 distinct cameras for every single match. It's designed to harvest a massive amount of visual data from every conceivable angle. You've got your main tactical cameras, spider cams sweeping in for those immersive aerials, ultra-slow motion rigs shooting at thousands of frames per second, and even referee point-of-view cameras.
But here's the crazy part. Those 45 cameras don't just stay as 45 isolated video feeds. The multiplier effect here is staggering. They instantly expand into roughly 150,000 network flows that are actively managed at the International Broadcast Center, or the IBC, down in Dallas. The sheer, overwhelming scale of data converging inside the network is exactly why this whole event is fundamentally run by network engineers.
And to put that data volume into perspective, we aren't talking about your standard compressed internet video here. A single second of just one of these camera feeds generates over 530,000 network packets. That is pure, raw, uncompressed pixels. We're talking over 5,000 megabits per second of data for a single feed just to ensure the picture is absolutely flawless before it ever even reaches a broadcaster.
But hey, the data journey isn't just about the video, right? Let's talk about the actual ball itself. There are microchips tucked right inside the match ball that transmit highly complex telemetry data 500 times every single second to off-site algorithms. This telemetry is perfectly time-coded directly to the live feed, which means video assistant referees can make decisions on an absolute razor's edge based on real-time physics, not just what the human eye can catch.
So let's move into Section 1, the fiber optic highway, specifically layers 1 and 2.
To actually build this highway, every single stadium relies on 3 completely diverse 200 gigabit per second fiber connections to securely transport all this traffic down to the IBC. These are massive, incredibly high-capacity pipes. Now, you might be wondering, why go through the expense and effort to lay 3 distinct lines for every single venue?
Well, because out in the real world, unpredictable disasters happen. You could have the most sophisticated software on the planet, but it literally means nothing if a construction worker halfway across the country accidentally drills straight through your critical fiber optic line during a live match. And believe it or not, physical fiber cuts actually happen pretty frequently, which is why having that physical redundancy is an absolute must.
To combat this, they use a genuinely brilliant redundancy system. The network doesn't just send one stream and keep a backup on standby. No, they actively send identical red and blue packets down completely different physical fiber paths at the exact same time. When the packets hit the destination, the system simply uses whichever one gets there first. If a fiber line gets cut, the broadcast doesn't even drop a single frame because the other packet is already there waiting.
Which brings us nicely to Section 2. The IBC and multicast magic at Layer 3.
Now that our data has finally reached the broadcast center, we face a massive distribution challenge. Think about it. If you have 100 different broadcasters who all want the feed from camera A, sending 100 individual streams would just instantly choke the entire network. So instead, they use IP Multicast. It's kind of like a firework. The camera sends just one stream into the network, and the network itself explodes that stream outward, duplicating it only exactly where a specific broadcaster has requested it. It saves a massive amount of bandwidth.
And managing all this chaos, that's a custom software platform called TFC. This system basically has a God's eye view of the entire network. It dynamically orchestrates these massive multicast flows across heavy-duty Cisco Nexus switches, statically configuring routes via gRPC to make sure those red and blue streams always take unique paths. This is software-defined networking operating at the absolute highest level.
To really grasp the awe-inspiring scale of this Layer 3 operation, just consider this. Capturing a mere 27 milliseconds of a single camera feed takes a mind-bending 10,000 network packets. And the network has to accurately route millions of these packets every single second without a single microsecond of noticeable delay for the entire 90-plus minutes of the match.
But of course, behind all this tech is Section 3, the human engine.
Because driving this entire technological marvel is, well, actual people. It takes anywhere from 250 to 600 dedicated specialists working tirelessly at the IBC just to execute the broadcast for one single match. We are talking about directors, audio engineers, graphic designers, and replay operators acting like high-tech conductors, staring down these glowing walls of incoming streams. Back in the 90s, all these teams would be stationed right at the individual stadiums. But today, by centralizing all these functions at the IBC in Dallas, they guaranteed total global consistency. The shaders, who are manually matching camera colors, the engineers mixing the 5.1 surround sound, the teams furiously scrubbing through replay servers to find that perfect slow-motion angle, they are all under one roof, live editing a completely cinematic broadcast in real time.
You can really see the absolute synergy of all this tech when you look at the audio mixing. As that smart ball moves around the pitch, the system actually knows its exact location and automatically boosts the specific ground microphones closest to it. That is exactly how you get that perfect, crisp sound of the boot hitting the ball right in your living room.
And get this, the engineering team even has to solve for physics. Audio data is much lighter and travels a lot faster through the network than uncompressed video. Because of this, the communications engineers actually have to intentionally delay the commentator's audio feeds. If they didn't do that, a commentator might shout, "Goal!" a fraction of a second before the video actually shows the ball crossing the line on your screen, which would completely spoil the moment.
All right, let's bring it all home in Section 4, layering it together to reach your screen.
For the final leg of our journey, this completely synthesized master feed hits the ultimate network. This whole operation is honestly an absolute masterclass in the OSI networking model. Layer 1 physical fiber optics are transporting the raw pixels. Layer 2 VLANs are segmenting the critical broadcast data away from everyday operational noise. And Layer 3 multicast and BGP routing are efficiently distributing those final streams globally to national broadcasters, who then push it over the very last mile to your TV or smartphone.
But you know what is perhaps the most astonishing fact about this highly resilient, mission-critical network? It is entirely temporary. It takes years to plan and months to physically build. But the very moment that final trophy is lifted, this massive data center and all its network infrastructure gets packed away and completely dismantled in just a matter of weeks.
Ultimately, the best way to really appreciate network engineering isn't by looking inside a rack of flashing switches. It's by watching one of the world's biggest live events unfold seamlessly across multiple countries, connecting billions of viewers without dropping a single second of the action.
So, the next time you tune into the 2026 games and see a striker find the back of the net, I want to leave you with this. How will your appreciation of the game change, knowing about the massive, light-speed data journey happening right before your eyes? Thanks for hanging out with me for this explainer, and keep that curiosity alive.